you very much, Claudia. So I have to, before I start my talk, I will give you a thank you and an apology. So thank you very, very much, especially to Claudia and the rest of the organization committee for giving me the opportunity to come to this wonderful conference and this beautiful city. I had really planned to learn a lot. This brings me to my apology. Just a couple of hours ago, I learned about a family emergency, so I do have to head out earlier. So apologies for changing the program on you. However, as Claudia mentioned, being the absolute expert on stochastic planning, this is an agile and resilient conference. So that was very fortunately facilitated. Thank you to Wellington for swapping with me. Okay. Now, my talk is pertaining basically to a market clearing mechanism for electricity markets as the penetration of renewable energy is increasing. So given that this is a bit of a mixed audience, some of you are very much experts in this field and some of you are more experts on the control side, I thought that I would go with a very brief and quick sort of introduction that would capture the highlights of what is needed in an electricity market, and then continue from there and mention how we're proposing to change the electricity market clearing mechanism and why do we believe that this is a superior mechanism given that it takes care of stochasticity. The very basics of electricity markets, as soon as you start basically talking about an electricity market to an audience, such as a graduate level program, the very first thing that you put up is this formulation of what's called a direct current optimal power flow problem. Effectively, what's happening is that one wants to meet the needs of the system, in particular the demand via some generation, and we want to do this in the most efficient manner, except the usual economic principles of basically having a supply curve and a demand curve and looking to see where they meet and having that clear the price don't quite apply here because the market is over a network. That's what makes it challenging, and it's also what makes it very interesting. So ever since, oh gosh, probably 50 years ago or so, actually probably no, it's maybe 40 years ago. So Fred Schweppe in his book, Nodal Pricing of Electricity, basically came up with this formulation here that says what we're trying to do is we're trying to meet the needs of the system at minimum cost, but we are respecting the fact that the demand must be satisfied subject to these flow constraints. So we're capturing the flow of electricity over the network. We are also taking care of what are called Kirchhoff's laws that basically say some of the flow around the loop scaled by the impedances of the electrical lines would have to be equal to 0. Now what I've ignored here is that first and foremost I'm dealing with a deterministic set of demands and generation, and secondly I've ignored losses in this system. So in terms of the notation, basically C is the vector of costs, X is the vector of generation of electricity, F is the vector of flows, A is a node arc incidence matrix that tells you what's going in and what's going out. This M here maps the tranches of electricity that are offered at any point in the network to the specific location of that particular node. And that's why it makes it basically converts the generation offers compatible to the network and this node arc incidence matrix here. Else the loop, we're basically ensuring that our flows are not too high or not too low, so they're respecting the thermal capacities of the lines. And we're also ensuring that each tranche of electricity complies with its lower and upper limits. So the way it works in an electricity market is generators basically offer in a number of megawatts or megawatt hours at particular prices. Now, there are some, so this is basically the notation in the previous slide that I very quickly went over, but it is available through the slides. some of the attributes of this market clearing mechanism that are very desirable are the fact that this market clearing mechanism is revenue adequate, and it's also cost recovering for the participants. So you are getting a number of generators to come in, generators of electricity, often at quantities, offering their quantities at specific costs. Then the market clears based on this optimal powerful problem, and nodal prices of electricity are determined here, as well as the optimal dispatches for each of these tranche X. These prices have some special properties, okay, for this particular market mechanism. And one of the sets of properties here is that these prices are revenue adequate, which means what the system collects, so the demand at each node is charged that nodal price of electricity. The price that's collected is more than enough, so greater than or equal to what is necessary to pay for each tranche of electricity that's offered in at each node. Okay? This is quite an important property because as a market broker, you don't want to be out of money. You don't want to have to pay out of pocket to any of the generators or have to tell them, well, actually, you're not going to meet your costs. Okay, so how do we prove revenue adequacy? Here it just very simply follows from linear programming duality. Okay? It isn't pertinent that the problem that we're looking at is linear. What is pertinent here is that we have a convex program. So this easily generalizes to a convex version. What is the next property? The next property, which is also quite important, is that as the generators are paid the nodal price of electricity, so you see there's this pi basically rearing its head again, that's the shadow price at each of the different nodes. We are mapping that shadow price and paying it to the proper generator who was offering in at that particular pertinent node. What we want to ensure is that the payment to the generator is in fact more than their cost of generation or equal to it as they have signaled. Okay? So this concept is called cost recovery, and this concept also comes very easily from the same linear programming duality, also generalizes to convex programs for the particular DCOPF that we showed here. Okay? So keep this in mind as we're going along. There's some properties for market clearing that are absolutely necessary and we really can't do without. Okay. Now, what is the premise for the new model that we are proposing here? This model basically rests on two key points. One is that there is a growing need for flexibility, okay, as the penetration of renewables is getting larger and larger in electricity systems. And the second one is that short notice deviations from pre-dispatch to the various generators actually incurs them costs. Okay? So I'm going to open up a small parenthesis here for people who are experts in the energy field. Often generators, in fact invariably generators, put in supply function offers. Supply function offers are designed to deal with uncertainty, but this is an uncertainty over a long-term horizon. So you're basically saying if the demand changes from one estimate to another, so long as I have prior notice to it, I can position myself to meet that demand at a price which is cost effective for me. Okay? This cost here, the cost of short notice deviation, is something which is unforeseen in that supply curve. So this is basically telling a generator, ramp up, and then 2 minutes later saying, okay, now ramp down by 50 megawatts. And then 2 minutes later, ramp up by 80 megawatts. That's the kind of thing that can happen, especially when you have a large amount of wind in the mix. Okay, so this is, I'm certain, very familiar to at least some people in the audience. It's called the duck curve. So I'll spend a couple of minutes just talking about this duck curve and then move on from that fairly quickly. It basically depicts the net load, so the net load is denoted on the vertical axis, as a function of time of day. So you've got 24 hours in a day. It's put out by the California Independent System Operator, okay? And the net load basically consists of load minus the amount that's met through renewable generation, okay? Renewable generation being either wind resources or solar resources or other sort of volatile renewable resources. And as you can see, as the years progress here, the different colored curves pertain to different years. As the years are progressing, the belly of this duck is getting fatter and fatter. And the difficulty with the belly of the duck getting fatter is that this minimum point, okay, in terms of net load, which incidentally is not too far away in terms of the number of hours from the maximum point, okay, is getting further and further away in terms of the absolute net load difference. So what this means is that there is a huge amount of stress in the system in terms of ramping up very fast and going from a period where the net load is quite small, well, relatively small here, to one that's about twice as much as what it was before, okay? So this is the one picture that I put up, which I hope will say the 1,000 words in terms of the need for growing flexibility. Also, keep it, yes?
I'm sorry, this makes sense for a certain time zone, right?
Yes?
So couldn't it just be offset by moving electricity across time zones, or is that too...
Okay, that's a good question, but how would you answer that for a country like New Zealand? Okay, so we're basically an island nation like that, and we're not connected to anywhere, right? Nearest country would be 3,000 miles, and we can't run a cable under the ocean. So to some extent, yes, you're quite right. You can mitigate this through time zone effects. But either geographical isolation or other impedances to rectifying this still maintain this very much as a problem. Okay? Thank you. Okay, so renewable, okay, sorry, just wasn't finished with the duck yet. Okay. The other thing here is that this is an average picture, right? This is an average day that we're depicting here. There is also uncertainty around the different amounts of net load for the different times of day, okay? So that makes the picture even more exacerbated. Okay, so high level of uncertainty in the forecast of the pre-dispatch of generation is likely to be inefficient. Expensive real-time adjustments must be made to meet the variations of the forecast. So you look at those two elements, and if you have a stochastic programming perspective, the immediate answer is, why don't we look at the distribution of the events in the future and try and make decisions in a more intelligent manner so as to facilitate system costs and make them minimum. Okay. So we'd, of course, been grappling with this problem for quite a while, and really the reason for that is that New Zealand does have a very clean and green image, and the penetration of wind was becoming rapidly more and more in New Zealand. So this was very much sort of on the forefront of our minds. We were concentrating on this problem 2007, 2008, and then we proposed a paper that finally came out in operations research in 2010 that set out a model. So let me jump to the model and try and explain it a little bit. That said, okay, remember that deterministic DCOPF that we had? Well, let's take it and turn it stochastic. Now, how do we turn it stochastic? We still have notation in here that says in real time, so this set of constraints in here pertain to real time. In real time, I have to meet the needs of the system while complying with network constraints. Okay, so the key notation here that should probably be explained is this tau sub n of f. It's the function that's basically looking at the sum of the outflows taken away from the sum of the inflows into a node. Okay, so it's slightly more concise and more general version of having the node arc incidence matrix there. Okay, This is my vector of real-time generation. I'm being a little bit sort of general here in the sense that I'm allowing for demand to participate in this market should they want to. They can cut back at a price, okay? It is possible to also have inflexible demand. We do accommodate that in this model, okay? And again, I've got my vector of real-time flows here, okay? Now, the obvious question after that explanation is what's the little x and what's the little f? So in our original model, which is depicted here in 2010, what we were thinking was we make a provision ahead of time before seeing any of these scenarios omega, right? So we don't have any realization here. This is a first stage decision. And in that first stage decision, we want to make sure that we're, quote, meeting the needs. Now, where the needs or the estimate of the needs coming from, the estimates of the needs are very much coming from the second stage here, okay? So it's remaining flexible. We're not making up an expected demand and pushing it up there, okay? However, we are making a decision, little x, and we are having some flows, okay? And we are ensuring that the network is in balance in the first stage, okay? That first stage is going to have some kind of a price attached to it. It's coming basically from this constraint. And then the second stage, under each scenario, omega is also going to have associated prices, okay? That come from meeting the needs of the system under a particular realization omega. We have the same set of constraints as before in terms of our vectors of generation having to be in a set, a bounded set where we're not generating any less than 0 or any more than the actual offered quantities, and also ensuring that our flows comply with any set of constraints that are on the flows so long as we maintain a convex program, okay? Now, why did we think of this? Oh, sorry, I also have to tell you about the objective function here. So the other piece that I didn't mention is the objective function. We have the cost of generation configured here, just like we had before in a deterministic optimal power flow problem. But what's added to it is an additional cost, which is the cost of telling a generator ramp up quickly and ramp down quickly, okay? Now, if a generator or a demand is inflexible and they can't do this, those costs are effectively set at infinity, okay? Yes?
On that constraint, in fact, you are asking that in the second stage, the corrective measures also adapt to 0, right?
Exactly, yes.
Okay.
That's exactly right.
And where is the uncertainty of the demand there? Where is hidden, or there is no?
No, there is uncertainty. So that's a good question. So some of it comes through this capacity over here. Okay. So that could be dependent on omega. You could even have thermal line capacities that are dependent on omega. So that would facilitate generation cap for like a wind generator that would be estimating to have maybe 50 megawatts, but then all of a sudden have 30 megawatts. Also for demand uncertainty and also for network uncertainty here. Okay? Okay, so that's a very good point. I should try and make those sets. So the C sub t here and these u's are actually a function of omega. I should probably make that explicit. Okay. Now, these terms, P plus and P minus, these are effectively the penalties that are coming from having to ramp up or down from a kind of a pre-dispatch position. So what we can think of when we look at this problem is that we tell the generators, this is basically what we want you to generate, but then proceed to real time and adjust that to this capital X sub t, okay? So then there's a deviation between those quantities, the real-time dispatch and the pre-dispatch, and on that, we would have to pay penalties, okay? And keep in mind these prices here. Now, why did we think of this? It kind of seemed natural because we felt that a first stage nodal price pi 1 can be interpreted as the marginal cost of serving a kind of a deterministic load. So if in every single scenario the load were to go up by 1 unit, okay, that would cost the system pi 1, okay? And of course, in node n, it would be pi 1 n. So it was appropriate, it was a kind of an appropriate price for a contract, if you would like to think of the first stage as a contract for differences. This would be an appropriate price for it. On the other hand, the pi 2 would be interpreted as a marginal cost of serving an additional node in that particular scenario, omega, okay? And therefore, this would be an appropriate thing that would get paid to the generator based on the deviation. So this was the model set up for the payment, okay? So we would basically pay the generator their pre-dispatch quantity here, little x, times the pi 1, plus the deviation multiplied by the pi 2. And if you rearrange this, you would obtain this expression down here, where it kind of more reflects the little x as a contract for differences, okay? So this was the thinking behind our original model. So we went through and we explored this. I'm going to skip this slide unless people have any questions on it, in which case I'll come back, okay? So then we started asking some questions about that model, and one of the things that we asked was, is this actually a revenue adequate market clearing, okay? So is what we're collecting the same as what we're paying the generators here? And the answer to that is, it's not the case under every scenario. So there may be some scenarios for which, when we collect, it's not sufficient to pay the generators. However, we did manage to establish a result that said, in expectation, we do maintain revenue adequacy here, okay? So we have an example, a very small example in our 2010 paper that shows that with a 2 scenario, so 2 demands, D1 and D2, in a 2-node network where you've got some cheap hydro and flexible, and you've got some expensive hydro but flexible, and a thermal unit that's inflexible, you would be able to set it up in such a way that under the first scenario, you would have a deficit of $7.6, okay? So here, your first scenario is you're going to be out of pocket, but of course, if scenario 2 occurs, then there will be additional payments, and in expectation, that's all good, okay? Now, other attributes of the model, such as cost recovery, I don't believe that this model is a cost recovering model, okay? There is a result in the literature that establishes expected cost recovery, but it actually ignores these penalties, little r's, okay? So the penalties of adjusting upward or downward. So the paper effectively argues, it's not one of our papers, someone else's paper. Paper basically argues that these R's are artificial, and to me, that's quite the wrong approach here, because the ramp up and down costs are in fact what this model hinges on. If those costs were not to be there, then having a supply function would be quite sufficient to capture all the differences in the system. So short-term deviation costs are in fact important. That's what derives this. Okay, so I have a couple of Norwegian colleagues, many of whom know, many of you would know them. And they are Mette and Endre Bjørndal from University of Bergen. They came to visit us last year, and they asked a very good question. They said, don't you think that when you're setting up this problem, you are only configuring the first stage decisions as an advisory or sort of a notice to the generators to where they should be positioning themselves? And if that is the case, then why do you worry that network flow constraints are complied with in the first stage, right? And in hindsight, that's a perfectly obvious question to ask. If you are looking at it from our perspective, I kind of already explained that the shadow price for this constraint is the price of capturing the usage of one more unit of electricity under every scenario that's going to ensue in the future, right? And we were looking at this from a contracting perspective. So we kind of needed a right price to pay the generators for these X's that we're effectively entering into a contract mode with, right? But if we are not having a contract, if we're basically just telling them, look, that's where you should position yourself, but I reserve the right to take you up and down from that, of course, with the acknowledgement that I would have to pay you a cost for this, then there will be no need to have this particular constraint here, okay? So as a result of Mete and Endra's visit, we decided to get rid of those constraints, okay? So now, if you're looking at this problem, especially in a nice, simple LP setting, what you see is that this first stage decision, little x, does not have to comply with anything effectively, okay? And I can assure you that by the end of the talk, I can get rid of these two constraints down here as well, okay? The only thing that I've got here that has anything to do with this first stage cost is noting to myself how much I'm going to ramp up by from this little x, or how much am I going to have to ramp down by from this little x in any realization omega, okay? And based on that, I'd have to pay a penalty to the particular generator, okay? There is no cost for little x. That's exactly right. So what happens in the end is that the total cost under the particular realization plus any costs of up and down, of course in expectation, is the total cost to the system. Incidentally, Claudia, if you rearrange the objective of the previous model, you would get exactly the same thing, okay? Because these U's and V's, you can rewrite them and pull out a cost component for little x out of it, okay? So the R is basically the cost, well, yeah, it's the penalty of deviation, but the capital X you can write as the pre-planned plus the real time, which is the deviation, and then you pull out the costs from that. Okay. Right. So now the obvious question is, how am I going to set my payment mechanism? Okay. I don't have a first stage, don't have a first stage cost, don't have a contract based on first stage. What do I do about the payment? Okay. And if you think about this for a little bit, an obvious answer comes to mind, and it says, okay, under each scenario omega, look and see what you generated. Okay, so X star here is the optimum real-time generation for the particular scenario omega, okay? And give this to the generators, obviously having collected the realized demand multiplied by the realized price from the demand side, okay? So everybody good with that? Yeah, yes.
Yeah, yes. Very often, the owner of the thermal plant is also owner of the renewable energy. And
Yes.
it looks like here, this kind of generator can play with the capacity at the first stage to increase payment. Second stage, right?
Okay. So I'm working, Alejandro, under the assumption that people are being truthful here, okay? If I want to look at gaming aspects, and we did look at gaming aspects in our original model, in our 2010 model, then I would have to try and build, for example, a Nash equilibrium where the market clearing is in fact a stochastic program. Now, as I mentioned, we did that for our first model, and the result was surprising because under the assumption of symmetry, we could analytically prove that the stochastic program will always do better than what's currently happening in a two-settlement system. where you would first say, this is what your dispatch is, and then you move on to real time and you change the dispatch on the generators, right? Because in the end, that is going to happen. You know, the uncertainty is there, right? And the generators will make their supply offer decisions given that uncertainty, okay? For this model, I haven't done it yet, but that's on the to-do list. So to build a Nash equilibrium for this to see what happens. How am I doing on time? 15 minutes? Okay, great. Okay, so first question, is this revenue adequate? Okay, and yes, it's revenue adequate. It's revenue adequate under every scenario because what you're doing is you're collecting the payments under a particular realization. So the collection of the payment is contingent on that particular realization, and paying it to the generators is also under that particular realization, okay? So everything here, 10 minutes, okay. So everything here basically falls back on that deterministic optimal power flow problem, okay? Because I'm doing it in real time, all right? For each scenario omega, okay. And in fact, we can go through this very same example that we had before, and we can look at the payment mechanism here, and we can see that under both of the scenarios, so total payments under omega 1 amounts to $122 and 2/3, okay, which is exactly the system revenue. And under scenario 2, the payments are $140. However, what I have collected here is $197. There is a difference between what I've collected and I've paid out. It's in the right direction for the system operator, so my system is revenue adequate. But it is more, and the reason it's more is due to this congestion rent. And congestion rent is something that people who work in electricity markets know very well. It occurs quite frequently in the deterministic setting as well. It's basically showing up here in the stochastic setting. Okay. Now, is it cost recovering? Okay. So here's a little sort of intuitive note here that says when I ramp some guy up, okay, so if the marginal tranche J, so that's the guy who was setting the price, if that marginal tranche J has been adjusted upwards, then the clearing price is the cost of the tranche plus the penalty, so to speak, okay, the deviation cost that's set from that particular tranche, okay? So in this case, it's pretty obvious that everything would be cost recovering, okay? On the other hand, if I'd had to adjust the tranche downward, then I'm kind of going slightly the wrong direction here, okay? If I consume one more unit of demand here, I would have to pay this cost, but I would save the penalty of having to get the guy to ramp down, okay? So what happens in terms of cost recovery? So if you make this note, then it becomes obvious that you can't have cost recovery in every scenario, okay? So what's the next best thing? Can we have it in expectation, okay? And yes, we can have it in expectation. We've got this proved not only for a discrete distribution where it follows from the stochastic programming duality going back to Danzig and Medansky, but also for the continuous case, very easily basically just falls out like this from the book of Shapiro, Rozhinsky, and Dencheva, okay? Okay, that's good. Because we are deleting these first stage constraints here, okay, we can show that the total welfare of the system does in fact get enhanced, okay? Sometimes it stays the same, but here's an example in which we do in fact get welfare enhancement. It's a small example. So you go through, you solve it, you'd see that with our old method, our costs would be 815. With the new method, it's 800. Okay. What are some of the attributes, some other attributes of this model? One of the nice attributes of this model is that this is very similar and reminiscent of the Newsboy problem, okay? basically what we're doing over here is we're ensuring that we are meeting the needs under every scenario, right? But there's penalties of deviation upward and downward from a advisory pre-dispatch location, okay? So what I've said here is imagine that we had this x omega, and the x omega was in fact the true optimal amount that was generated, the vector of generations under omega, right? So those are the optimum ones for once you solve the problem up to the end, okay? Now, if some oracle came and gave you those vectors of generation x omega that were the optimal ones, then our problem would in fact be rewritten as selecting this little x, positioning ourselves as the argmin of this expectation, given that x omega, which is the optimal generation, would basically be this advisory position, either ramped up or ramped down, okay? And I would be paying penalties on these. So you sit back, you have a look at this. This is in fact identical to the news vendor problem, okay? So the optimal solution, little x, is found by the same quantile method that the news vendor problem would be found by. So component-wise, little x is this quantile, which is Ru, again the correct component, divided by Ru plus Rb, the component. So these are being the penalties that set the cost over there, okay? And this is something that I haven't managed to use yet, but I'm very much hoping to be able to use to have a fast way of solving this problem, faster than Bender's decomposition. Okay, now the competitive equilibrium here is also equivalent to system optimization. So here's our system optimization problem. I've gotten rid of the network flow constraints in here, because if I have transmission here, then I would have to have an agent who's the transmission agent as well, okay? So in the simplest case, when I don't have transmission, then solving this problem is exactly the same as relaxing the demand constraint under the different scenarios, pulling it up into the objective with the correct multiplier, okay? And ensuring that the price that I've pulled up here is the right price for meeting the demand, okay? And once I have this problem up here, you can see that it breaks by different tranches, in fact, okay? It decouples by different tranche. So if each of the agents or each of the tranches are risk neutral and they are minimizing their costs in expectation, okay, and I take their problems and I couple them with this orthogonality condition that my price and demand would have to satisfy, then I've in fact recovered the system optimality problem, okay? So the competitive equilibrium here, and notice, Alejandro, I didn't say Walrasian this time. So, so that basically covers that attribute that the competitive equilibrium has the maximum social welfare. Okay, now a couple of notes. What if the agents are risk averse? I think this is a nice thing to think about. If the agents are risk averse and there's enough instruments of trade, then what happens is that the risk problem can be pulled and transferred into another expectation problem where the expectation is taken with respect to the same probability atoms, but the adjusted probabilities on those atoms so as to reflect the risk of the various agents, okay? And therefore, we're back to the same result as we had before. If the market is not complete and there isn't enough instruments of trade, then there is a theorem of the second best here, and that again comes to something which I hold is very similar to exercise of market power, okay? Now, the last time a few months ago that I put this result up, Tony asked me a question, and he said, what happens if you have a sample that you make decisions with respect to, okay? But you move on to real time and you encounter a scenario that you hadn't account of in your sample, okay? Which is an excellent question, and it's a problem that stochastic programming in general would kind of suffer from. But then again, there is a whole lot of machinery that Shapiro, Rosinski, Homem de Mello, Dencheva, a whole school of people have basically tackled, and they've developed this sample average approximation set of results that says, as you enrich the sample that you're encountering, well, of course, if you have a useless sample to start out with and you go out and you see a scenario which is quite different from that, then there is no hope. But if your sample is somehow rich enough that it's reasonably close to your distribution, then you can establish some really nice results here. Now, revenue adequacy, we knew that we had under every scenario, so we don't need to worry about it. The main theoretical result that we've managed to, in fact, get over the last month or so, and we've dotted the I's and crossed the T's, is that if we have a sequence of distributions that converge to a distribution mu, and I mean in the sense of distribution, then this function here, which is reflecting the revenue adequacy of the system, is a continuous function as a function of the first stage decision that I make, okay, and the distribution that I look at, okay? So asymptotically, I'd have expected revenue adequacy here, okay? Now, of course, because we are really hoping to be able to implement this and get some mileage out of it, what we need to do is test this in practice. We're fortunate enough that we have the whole of the New Zealand system in the form of software called VSPD replicated for us. We have information of every half hour of every day going back 15 years. So we've just developed the Bender's decomposition code, and I'm in the process of collecting all the information, such as what we would get from demand and what kind of payouts we would have, and looking at all those sorts of good things. So hopefully next time I give this talk, I'll have all those numbers there as well. So aside from looking at this from an implementability perspective and doing it for two-stage, another question that's kind of staying in my mind is how would this work if we want to extend it to multiple stages? Multiple stages would make sense for New Zealand because although information is collected over half hour, our system operator actually does the optimization every 5 minutes. So for those 5-minute bands, it may be more useful to do something like this, and we would have to potentially go up to 6 stages there. But we would have to basically work out how to do it. The other thing is trying to work out the special structure of the solution that I was talking about in terms of the news vendor to see if there is an easier, if it's sort of faster algorithm to do this. But I think that's all I have for today. So thank you again very much, and especially thanks for accommodating my change request.